Before I get to the main topic, I'll say a few things informally, just for motivation. So what we are trying to do here is, so I think Amit talked about it. So we are trying to, so x mapping to, so the direct sum of a kx. So where I've written this k upstairs, so k greater than equal to 0. So this is supposed to be a cohomology theory. So in particular, I mean, I'm not going to clarify what I mean by cohomology theory, but it's supposed to be a contravariant functor for each k. This ak of x is supposed to be a contravariant functor. So x going to akx should be a contravariant functor. So what this means is that given a morphism of varieties, we should be able to do a pullback, right? So the thing is that we don't, so far, I mean, I think we haven't actually gotten to that point in this workshop yet, but so we do have a pullback something like this. So f of a star from a k y to ak x if f from x to y is flat, but we would like to construct f upper star for a more general class.
You don't want to keep the same k, this right star.
Yeah, actually, that is better. Actually, k will be a field, so that will be more problematic. So, okay, now star is a problem. So,
because it changes.
No, there is a star here. So.
That k and that k are not the same k.
Okay, I mean, no, they are. No, upper, it's cohomology. Yeah, so, yeah, I mean, so, yeah, so this is, okay, maybe I'll just write L, not K. So, yeah, this is fine. That is not the problem. So, for a more general class, of morphisms. So, this is what our today's topic will be in aid of. I mean, it's just a sort of technical device to make this happen. So I'm going to have to use a couple of things as black boxes, so which will be done in Amit's lectures. So I will just clarify what we are going to assume. So we will assume. The following. There is this theorem. So, I mean, this is towards the end of chapter 2 in Fulton. So that let X be a scheme. So when I say scheme, I mean algebraic schemes over some fixed field, and let D be an effective Cartier divisor with f from D to X being the embedding. Then we have a homomorphism from, so f upper star from A, say M of, so now I'm shifting to this thing, so am of x to am minus 1 of d. Okay, so the difference from what Amit may have talked about so far is that I think he talked about doing this, I mean he talked about pulling back the divisor. I'm talking about pulling back to the divisor. Okay, so you have something like this, where, so given by f upper star of some, so if V is some m dimensional subvariety, this is equal to d dot V. Okay, so this is what I will assume. And also, if the normal bundle, okay, yeah, so I guess if D is smooth and the normal bundle of D in X is trivial, then f per star is the zero homomorphism. So basically what is going to happen is that this is because f upper star can be written in terms of the Chern class of this line bundle, and then the Chern class will be 0, and so this is something that Amit will do probably maybe hopefully within the next 2 lectures, maybe next lecture. So far, but this is, we'll just assume this, and this is going to be this is going to matter only at a very particular point. The rest of the lecture will actually be I hope somewhat interesting geometry. Okay, so this is where this is going. But okay, so now what is so what I'm saying here is that, I mean, we want to do pullbacks for a more general class of morphisms. I'm saying that I'm going to assume that I know how to do this for divisors, and from this the idea is how to do it for more general maps. So what we are going to do is basically construct an analog of the notion of tubular neighborhood in algebraic geometry, or at least for intersection theory. So yeah, okay, maybe I will get to the point now. So but I mean, okay, before I define normal cones, let me talk about something which is simpler. So tangent cones. So as an example, let's let x be a curve. Be okay, maybe, it doesn't matter to be, but okay, let's say that this is a curve in the plane given by the equation f of xy equal to 0, and assume that f of 0, 0 is 0. So it passes through the origin. So what do I mean by the tangent cone to x? So what? So suppose we write. So let f equal to fd plus fd plus 1, so on fn, where fi is homogeneous of degree I. Okay, so now the thing is that the polynomial fd, which is a homogeneous polynomial, is of interest to us, because what it really does is it's sort of near the origin. If you want to understand, roughly speaking, if you want to understand the behavior of this curve, you might as well ignore these higher degree terms and just focus on this. So so near the origin, the variety will basically look like the zero set of this, right? That's an approximate I mean, this is an approximate statement, but anyway, the polynomial, okay, assume for now, just for this particular thing, assume K algebraically closed, so that I can then factor polynomial FD xy factors into linear factors so FD of xy is equal to the product of, say, some hi xy. So maybe there are some repetitions. Let's say I equal to 1 to d. Now the thing is that if Li is the line hi equal to 0, then the intersection multiplicity. So it's something we have not defined, but it's something, in this particular special case, it's something easy to guess what it should be, of Li with x at 0 0 is higher than that of our generic line. So what do I mean by this? So if I want to define the intersection multiplicity of a line with a curve, so what do? You basically parameterize the line, write it as basically the points of the line are, say, given by P of t comma Q of t, where P and Q are linear polynomials in T, and then you plug that into the equation of your polynomial, and then the points of intersection will correspond to the roots of the polynomial that you get, right? And so this is how you can define intersection multiplicity for intersections of lines with curves. Then you can check that if I leave out these lines, any of these lines Li, then the intersection multiplicity will at 0 0 will be exactly d, and but for these it will be higher. Okay, so these lines, so the lines Li are called tangent lines. To x at the origin. Okay, and so the zero set of this product, this polynomial FD, the zero set of FD is called the tangent cone. Of x at the origin. Okay, so now can we generalize this to higher dimensions? So if so the same construction can be done for a hypersurface in AN. Okay, so if a hypersurface is given by a polynomial f equal to 0, then again you do the same thing, exactly the same thing, and then you get the notion of the. No, you don't do that. I mean, this was just to. I mean, I don't need to say or just talk about FD. Right? So I mean, here you can factor, but it's. This was just to talk about something familiar. Okay, so now we can do this for hypersurfaces. Now, can we do it for something that is given by by something that is cut out by an ideal which is not generated by a single polynomial? So more generally.
Chetan, so you have to perhaps add that the zero locus of FD is the one.
Okay.
The same construction will involve the zero.
Yeah. So okay. So if x equal to so I will use this kind of notation, 0 locus of f, where f is in k of x1 to xn, and say if f of 0 is equal to 0, then the tangent locus, the tangent cone of x at the origin is given by x at the origin is 0 locus of fd, where fd is the homogeneous non-zero homogeneous component of f with least degree. Okay, so now the thing is that so far, I mean, I've just talked about what this is. I haven't said anything about what it is good for and what we are going to do with it. But roughly speaking, I mean, it's something that tells you what the variety looks like near this particular point. And one problem with this definition is that it sort of depends on this embedding. I mean, it seems to depend on the embedding. But there is an alternative description of this. So one can prove that. Okay, actually, I haven't. I need to say a little more. So what can we do more generally? More generally, suppose f is equal to the 0 locus of I, where I is an ideal in k of x1 up to xn is an ideal. So what is the corresponding thing that we can do over here? So you could this thing about taking the lowest degree term, lowest degree homogeneous component. So let's define that. So if p is in k of x1 up to xn, I will define the initial form of p equal to lowest degree non-zero homogeneous. Yeah, sorry. X. Non-zero homogeneous component of P. So then what I can do is I can take the initial component of each polynomial in F and see the ideal that it generates. So it is not enough, for example, to take just a set of generators and take the initial form, because there may be some cancellations. So we define in I is defined to be the ideal generated by in P for P running over all the elements of I, P not equal to 0. So yeah, I guess I should say P not equal to 0 here. Then the tangent cone of x at the origin is the zero set of the initial ideal of I. Okay, so this should be a familiar construction to some at least. So now, as I said, the problem with this construction is that it is depending on the embedding, but we can improve on that. One can prove that the tangent, so okay, I mean this is at the origin. If I want to define it somewhere else, I can shift the origin and get it done. One can prove that the tangent cone of x at a point x is isomorphic to something that can be defined more intrinsically to a spec of the graded ring of the local ring at of x at little x, where so this graded ring of x is the ring direct sum of mx I mx is 1 I equal to 0, where mx equal to maximal ideal of OXX. So this is not immediately obvious, but it's not difficult to prove. So maybe if you want, we can check this during the discussion, or so just just so that, it's not difficult to prove, but just I'll write a reference. So this is you can see Mumford's Red Book. So there he works this out. Anyway, so the point so the advantage here is that this is intrinsic. Now the question is, suppose I replace the point x by a closed subvariety, then can I do what is the natural construction to do? So that is the normal cone. So my whole purpose in discussing all this was to motivate normal cone, and I thought this would be a natural object to start with. But okay, so now before I write down the definition of the normal cone, what are we going to prove in today's lecture? So as I said, what is our intuitive understanding of why this should be useful? It is because when you look at x very near the point little x, this is basically what your variety looks like. Okay, so that's how we think about it. So so what we mean is that if we take this variety and zoom in closer and closer, then ultimately you should get this, okay, in the limiting case, and that is exactly what we will prove. Well, that's roughly the kind of result that we will prove. So the idea is that suppose you want to do some calculations with suppose you have got a variety y and a subvariety x, and you want to do some calculations in some intersections of x with something else, then it seems reasonable that maybe you don't need the whole of the variety y. Maybe some kind of a neighborhood of y should be enough. And so what should that be? So in differential topology, given a manifold and a submanifold in it, you can construct something called the tubular neighborhood of that, right? So then we want to do something like that. So any problem involving the intersections involving the closed subvariety can be transferred to the normal cone of the subvariety, and then you can do the calculation over there. So that is basically where we are going with this. So what are we going to do? To say that these two problems are sort of equivalent, we will basically construct a recipe to go from y to the normal cone of y at x. To say that they are kind of equal, we want to show a flat family which takes this embedding of x into y. You can deform it through a flat family into the embedding of x into the normal cone of y at x. Okay, so that's what is going to be the main result. Okay, so now let me write down the definition of the normal cone. Definition: let X, let Y be a scheme, and X if Y a closed subscheme. Say given by a sheaf of ideals I. Okay, so I. So then the normal cone of Y. Okay, now I forget how to write this. I mean, is it normal cone of Y or at X? Okay, normal cone of Y at X. So denoted by CXY is defined to be the X scheme spec of I, of the direct sum of I to the R by I to the R plus 1 R. So if you look at this particular thing, so whatever the construction that I had written for the graded ring of a local ring, you can do that in general. So given a ring and an ideal, you can write down some kind of a ring like this, and then you can do it for a sheaf also, right? You can do you can sheafify that construction, and then so this is now going to be a sheaf of OX algebras, and then you can take its spectrum, which will give you a scheme over X. So this is the object that we would like to use today. So this is the normal code. So okay, so this is the main object. Now, before we go any further, let me start by recalling some material. So much of for some time, I think the stuff that I will say will be very familiar. It is basically from the second chapter of Hartshorne, but I think it will be good to revise it quickly. So, in general, what is a cone? Let S dot. So let's say that X is a scheme. So again, my schemes are algebraic schemes over a field. Let S dot be a sheaf of graded OX algebras. Say S dot. So this is they are like this. So S0 direct sum, S1 direct sum. So these are all just sheaves such that so one. S0, so okay, OX to S0 is an isomorphism. Secondly, S dot is generated as an OX algebra by S1. And thirdly, S1 is a coherent OX model. Okay. Well, it is generated, isn't that going to? That doesn't imply that. Yeah.
You can take J lower sheet of
No, but doesn't
I know that rules don't say it, but then that's a mistake.
I see. Okay.
Where did he say? So now you can simply say Sn is square.
Okay, fine, fine. Okay, for all. Okay.
Is it Sn quotient of S1 and the S1?
Is the quotient of coherent with coherent?
On the invariant scheme.
No.
I thought it is actually. I mean,
You take an open subset of affine line and take J over sheet of OU.
If it is quasi-coherent, then it is coherent.
But you have not said that.
So you should first say quasi-coherent, then it
It's
is.
okay. You are not against Sn.
Yeah, it's okay.
So say that.
Star. Suppose star is the X scheme spec of S. Okay. Then so in general, when I say cone over X, I mean the cone of some graded algebra like this. So a cone over X. So this is one thing you can do with this. Another construction which should be familiar is that the projectivization. Okay, so C. So suppose I have a cone. So if C equal to spec S star is a given cone, its projectivization is defined, so denoted by PC is the proj of this. Okay, so we are going to have to do some calculations with this. So I hope it is that people remember what this is. So this is so as a topological space. I mean, as a set, what do you do? Basically, you're taking homogeneous prime ideals, except for the irrelevant ideal, and then you set up. Then you basically give it a scheme structure.
So those are line syntax. Line syntax.
Yeah. Okay, and so I'm going to assume that everyone understands what is the basis for this and so on. So the projective completion. Okay, so one thing is that see, if I give you two cones, I can always take. So if C equal to spec S dot and T equal to spec D equal to spec T dot are cones, then spec S tensor OX T dot is a graded algebra, graded OX algebra. So where the grading is sort of the usual one. So S dot tensor OX T dot. So the nth piece of this is the direct sum of SI tensor J OX I plus J is equal to n. And then C cross D over X. So the fiber product of this is a cone, and we write it as the sum of these two cones. Okay, so in particular, you can do this by after taking D to be just the trivial line bundle.
You want to mention that spec of this is this.
Oh, did I not see that? Okay. Yeah. Okay. In particular, so if we take, so let 1 denote the trivial line bundle. Okay. Maybe before I say this, so the thing is that a basic example of this is vector bundles. So example. So let M be a coherent OX module. Then we can apply. Then we consider. Then the cone of M is okay. So I can take the symmetric algebra of M. So so spec of S of M. So this defined is the cone of F of M. And if M is locally free, then this is a vector bundle. So cones are basically generalizing the notion of a vector bundle.
But just say this is the vector bundle M blue. This is the vector bundle that's called M blue. These sections are in blue.
Yeah. So actually, that is. So if you have any OX module homomorphism from M to OX will give rise to a OX algebra homomorphism from SM to OX, which will give you a section of this vector bundle. So the sheaf of sections of this vector bundle is M dual, which is Hom of Hom OX of M. Okay, so this is one basic example. So now in particular I can take, so in that construction of the sum, I can take one of the cones to be the trivial line bundle. So let 1 denote the trivial line bundle over X. So if you look at P of C plus 1 is called the projective completion of C. So this will actually contain C as an open subscheme, and so let us see what this looks like. So if C equal to spec of S upper star, so then what am I looking at? C direct sum C plus 1 is the cone of the graded algebra T, which is S well, I take S and I take the polynomial ring in one variable over this, like this. So Z is a variable, and so then Tn looks like what? It looks like Sn plus
What's the degree of Z that you say?
Of degree 1. So this will be Z times S n minus 1 plus so on Z dn S naught. So then, so we have a surjection. So sending. So we have a surjective homomorphism from T to S, which basically sends projects everything to this thing, just sets Z equal to 0, and so which such that which sends Z 0 and maps Sn to itself. Then so this gives this gives an embedding, gives a closed embedding of PC into P C plus 1, and so using the notation in Hartshorne, I suppose this is standard notation. So if I look at this, so this is the open set where Z doesn't vanish. So this is isomorphic to C. So this is, you can do this as an exercise. So the point is that this is exactly like what we do with, for example, when we go from affine space to projective space, is exactly the same thing that is happening over here. Let me also look at blow-ups. So this is again something I'm not going to do it in complete detail. I'm just reminding you that so let's say that X is a let me say that let's Y is a scheme, and X Y is a closed subscheme. Given by an ideal sheaf say I, then the blow up of Y at X, denoted by X Y is the Y scheme okay, so this should be familiar. So I will need a few things about this, some explicit calculations. So one thing is that writing this like this is not incorrect. It is a little bit confusing because
Why should an operator scheme write I to be coordinate scheme?
just What do you mean?
I to be a coordinate sheaf and
Yeah.
Y to be an algebraic scheme.
Yeah, these are all algebraic schemes. So that is the standing assumption. What I was saying was that this is a little bit confusing to write with, because when I say the ideal I, do I mean the one in degree 1, or do I mean the one that is sitting inside the degree 0 part? So this kind of thing can, at least it sort of upsets me a little bit. So what one can do is that we can also write this. As proj of you can just write this as you can take u to be a variable of degree 1, and you can just write this as I to the r, so times u to the r, where r is greater than or equal to 0, where u is a variable of degree 1. So what is, I hope this is clear. So this is actually sitting inside, so I to the r, u to the r, this is sitting inside the, so r greater than or equal to 0, this is going to be sitting inside ox of u. Okay, so I think this will help clarify what we.
Keeping becomes clear.
Yeah. So what I'm going to need is something very simple. Okay, what are blow-ups? What are the standard properties of blow-ups that I think everybody knows? So one is that if you look at the idea, so this is the blow-up is sitting on top of y. So if I look at the pre-image of x in the blow-up, that is going to be a Cartier divisor, right? So it's going to so I basically becomes a invertible sheaf when you go upstairs, and also there is a universal property that basically anything else where this happens has to factor through the blow-up. So I will assume that everyone knows this, and I don't want to spend time writing it out. But so let us talk about, so if pi, the blow-up is sitting on top of y like this, so what is pi inverse of x? So E, the exceptional divisor, is pi inverse of x. So what does this look like? E is defined as the zero locus. E is the okay, it's not defined, it is the zero locus of I on the blow up x y, and so it is given by, so it is the zero locus of I to the r plus 1, where r is greater than or equal to 0. So this particular ideal sheaf. Okay, and so what is?
You want some notation to indicate your.
Yeah, sorry. You want me to write it like this, or is,
No.
then?
It's the locus of an ideal sheaf, but the ideal sheaf is downstairs. Then you will pull up the ideal to the blow up and take it.
So this corresponds to the Cartier divisor of the invertible sheaf.
That
No,
I
one
was
second.
the sheaf downstairs.
Yeah.
What's the name of the sheaf upstairs? Is remember.
Yeah. So
P inverse I of the
yeah. Pi upper star of, well, pi upper star is.
It's not exactly.
Yeah, it is not. So pi inverse is better. Yeah. Yeah, I know. Yeah. Yeah. Times O of the blow up. So this is this is equal to the direct sum of r greater than equal to 0 of I to the r plus 1. Okay, so now the thing is that so this is so if I took this this thing, and then if I were to shift it to the left, basically I would have OX in the -1 degree, and then I would have this, right? But okay, what I want to say is that what is the if I take this graded module, what is the graded quasi-coherent sheaf associated to it? So the thing is that if two graded modules give you the same sheaf if they match up in higher degree, right? Sufficiently high degree. So what that means is that this is this is just the quasi-coherent sheaf associated to let's see. Yeah.
What it is two sides have some ambiguity in that last equality. The sheaf is on the right hand side.
Yeah,
You are still downstairs.
So you
Yeah.
want to say it's the
I could write it like this.
And tilde. No.
You want upstairs. This is still downstairs.
Oh yeah. Okay.
No, but that thing is the sheaf. I mean, when you direct sum of I to the power r plus 1 is the sheaf of OX modules, right? Sorry, OY modules.
You want the upstairs sheaf.
Yeah.
No, this is why is
This
this?
equality is taking place on what space?
Lower, right?
See, this is an ideal sheaf in this graded algebra, right?
U lives upstairs.
Yeah. U lives upstairs.
No, so but this is a graded ideal, but you have to take the tilde to get a sheaf.
Yes.
The tilde of that.
Yeah, so that's what I'm saying here, that the quasi-coherent sheaf associated to this is basically O1. So I guess I should write the blow up. That's why. So it is inverted. So it is inverted. And E is a Cartier divisor. So what are the local equations of this? So that is what I want to see. So again, since I think I'll just write down what it is, and we can talk about it later if necessary. But I think this Y can be covered. By open sets of the form. Okay, let me. It sort of gets easier if I just assume that everything is affine. So let us assume. And I corresponds to the ideal I. So this can be covered by open subsets of the form D plus of say XU, where X is in I. Okay, and so now the question is, so dxu, d plus of xu, this is an affine scheme. This is isomorphic to spec of well, if I take okay, maybe I should write more notation actually. So S equal to direct sum So summation of I dr 0. So this is my graded algebra. So what I want to do is I want to take this and I want to take the degree 0 things in this, right? So then I will just state this as an exercise which we can work out if necessary, but it's sort of, it follows immediately from, so if you just look at the proof of the fact that, you know, the blow up has all the properties that we mentioned, this is just something that will come out of it, that so on b plus of xu, the equation, the closed, the divisor BL x divisor E is cut out by, is defined by, so what is the local equation? It is just x, well, x over 1. Yeah. Okay, so that is, so basically it has whatever was defining x now defines E. Right, that's more or less, that's exactly what you would think anyway, but except that now you only need this one particular generator on this patch. Okay, so this is what I need from blow-ups. So now let me define the deformation scheme. No. Why does it have to be? No, what do I need? I need x to be a non-zero divisor. Okay. Yeah, I'm just assuming it to be a. Yeah, maybe I need that, but okay, let's. So what we do is again. So maybe I need irreducible or something like that, but I will check. Maybe we'll talk about it in the discussion thing. So y is a scheme, and x in y a closed subscheme. So I will, let me just continue like this and take, let's say y equal to, say, spec A. So I mean, whatever I do over here can just be glued together, defined by.
So actually, if x is a non divisor, then d plus xu becomes empty. So homogeneous.
Yeah.
So anyway, that statement is actually true. So condition is actually true.
Yeah. So defined by the ideal I. So then what we do is we look at so we define m x y equal to be the blow up of y cross p1 at x cross, well, you could write x cross 0, but Fulton is doing x cross infinity, so I will do that. So that is, yeah, I'm not sure why he does that, but anyway, I just don't want to. So this is what we do, and now we want to see what is the exceptional divisor. We want to understand the exceptional divisor of this. So, well, not just the exceptional divisor. Okay, so we have the homomorphism. We have a so rho from m x y p1 is the composition.
See, he wants the variety at 0 to be the starting norm.
Yeah, I understand. But apart from that, I mean, okay, ultimately the calculation is now going to happen at infinity, so he will use a parameter over there. Is the composition mxy to y cross a1 to y cross p1 to p1. So this is a flat map. This is a flat morphism. So this can be an exercise which we can discuss if necessary. But basically, this is easy to check because this is a smooth curve. Okay, so now what I want to understand is what is rho inverse of infinity.
We are only saying the composite is flat.
Yeah. So this map is not flat. This is not flat, but
What this was not this.
okay, rho is flat. Now the thing is that this is almost the family that we want. So what is going to happen is that at over 0, I have just y and x is sitting inside that. Now when I go to infinity, I want to see what happens. So the fiber over infinity is almost what we want. It is going to be a union of the cone, but there is also going to be a copy of y sitting in there, which we have to discard. Okay, so that's what we want to verify. See, the thing is that y cross infinity, x cross infinity sits inside y cross infinity, which sits inside y cross p1. And so when I blow this up, so we get a closed embedding of so you take the blow up of y cross infinity at x cross infinity, so let this into the blow up of into mxy. Okay, and I would like to understand what this is. So let us denote the image by y tilde. Okay, then what we do is I think I failed to mention one important thing when I talked about the blow up. So about blow ups. I guess I got distracted along the way, but if blow up of, so this is, I mean, I'll have to sacrifice this notation and go back to my earlier notation. So this is the blow up morphism, the blow up. Then the exceptional divisor is equal to, so let me say this is pi, so pi inverse of x. This is given by, this is cut out on the blow up by the ideal I, which defines x, and so this is actually isomorphic. So if you write it out, you will see that this is isomorphic to the proj of the direct sum of I to the r by I to the r plus 1, where r is greater than or equal to 0, which is basically the normal cone. This was, it's unfortunate that I failed to mention this in time. But anyway, so this is something that I think should be familiar anyway. So we know that the exceptional divisor is the normal cone, which is what we wanted. Well, actually, that is this. Okay, well, it fits in together anyway. But I mean, it's the normal cone. It's the normal cone of x cross infinity inside y cross a1. So it will actually be the projective completion of the normal cone. So returning to my notation over here. The exceptional divisor of is isomorphic to what? So it is the normal cone of it is isomorphic to, you take the normal cone of x inside y, and then you have to do plus 1 because of the copy of, because all this is over y cross p1. And so this is this contains so as I said, this contains the normal cone as a open subscheme. So what I want to show now is claim that so rho inverse of infinity. So this is actually a divisor, right, on mxy. So this is equal to p of of c x y plus 1. So this is going to be one piece, and plus y tilde. And y tilde is just a copy of y. So what we will do is okay, so this is what we will do, and then we will throw this away, okay, and then that will give us the required scheme. So we'll okay, so let's just quickly see how to do this.
In fact, throwing away will throw out the intersection, and therefore it does the normal cone cy. So px, so e intersection y tilde is so what is this? This is basically p c x y. No, what am I saying? You're throwing away the part at infinity, taking the rest of the c x y.
No. Just no. Sorry. This is.
Think of vector space P of V x.
Yeah. But I mean, why is it intersecting? How does this sit inside y as a closed subscheme?
At infinity is this.
No, in y tilde. Y tilde is just.
Proper transform.
Yeah. But isn't it just a?
Is just a function of x.
Huh. Yeah. Okay. No, so they have to intersect in. I'm just confused, right? Huh? Yes.
And take the base x to be a point.
Yeah.
Now you have vector space V and space plus 1 and it's going to space.
Yeah. No, I understand that this has to be the thing at infinity.
Yeah. And that is the intersection of the proper transform with the intersection. So what remains is just c x y.
Yeah.
E minus this intersection equal to c x y.
Yeah. No, the reason why I'm slightly confused is that y tilde is isomorphic to y. So yeah, because no, it is not, right? No, it's not. What am I saying? Yeah, sorry. Yeah, okay, fine. Yeah, this is the exceptional divisor of this blow up, this particular blow. Okay, so yeah, so this is what I want to quickly verify. So what is so let's just look at local equation. So to prove this, what I will do is just compute the local equations for this and this. Okay, so so mxy can be covered by open subsets S so spec of S SA, where S dot is, this is just direct sum r greater than equal to 0, I comma, well, okay, so now since I am using that other notation,
Is that X tilde?
no, this is y tilde. Y is the bigger thing.
I'm trying to draw a picture.
Huh.
Can you draw a picture of this?
Okay, I mean, so the simplest case would be this one.
And that point is infinite.
Yeah, so then this will blow up, and then you will have this will be y tilde.
So there's this part which comes and meets somewhere, and there's that part which is moved away.
Yeah.
And an exceptional divisor is created, which is this.
Yeah.
That part which is the proper transform, the vertical thing you are going to throw away.
This is what I will throw away. Yeah.
Which is the proper transform of the vertical line.
No, so okay, so the way I'm looking at it is that this is y cross p1. So this is actually y cross infinity.
So the vertical part is
Not the vertical part. That I don't throw
the
away.
vertical part. Vertical part is x cross a line or something like that.
This is x. This is x cross p1. Yeah, that I don't throw away.
So
I throw away the strict transform of this.
you throw the transform of y cross.
Yeah. So rho inverse infinity is basically, well, I should have written this. Yeah, I will.
I was imagining the axis
Yeah.
interchange, so I
So,
was confused what you were doing.
I mean here so you asked this, right? So this is the flat pullback, right? So the pullback of just the preimage. I'm just looking at the preimage of infinity. So just the picture of what is going on here is that so let's say that my y is a line, and x is y is say a1 and x is the origin. Okay, then I take this line. So let's say that this is y cross infinity, and then this line that I have over this vertical line is x cross infinity, and I'm blowing up x cross p1, and so what I'm blowing up is this point, right? So we know what this looks like. So what happens is that you get an exceptional divisor like this, and
Exceptional divisor in your picture.
this one,
Oh, yes.
and this is,
Different drawing.
yeah, I guess so. So this is the strict transform of x cross p1. So I don't know how. Maybe I will write it as this. Okay, and then the strict transform of this is, it meets somewhere over here. This is my y tilde. Okay, so what I'm throwing away is this part. Okay, and then this, what is left over here of the exceptional divisor, is my normal cone. Okay, so what I was saying here was, so S is the sum, the grade I comma t. So t is the parameter at infinity. Okay, for on p1, and so I'm looking at this graded algebra, and so where this is and A is going to run over things in here. This should be r u to the r. Okay, and A is in I comma t u, right? So this is where I will do the calculation. So in D plus of AU, which is isomorphic to spec of S dot AU, I should have written AU here. E is given by, E is cut out by A over 1, which is sitting inside S0, right? And okay, so if in particular if A is in I, then so the local equation for E is A over 1.
Sorry, T is the coordinate of Q1.
T is
What is T?
yeah, okay, maybe I will write it over here.
Infinity is 1 equal to 0. Infinity is equal to 0.
Okay, so T is the parameter at infinity. So yeah, so if I have this, yeah, so I still yeah, this I know, but what does what about y tilde? So what is the homogeneous ideal defining y tilde in this? So okay, so how did I do this? So I have got so S dot is equal to the summation I comma T into the R. So I have this, and then so this gives me the blow up of y cross P1 over x cross infinity. Now, what is the corresponding thing for the blow up of y cross infinity at x cross infinity? So I'm going to get the algebra I to the R, u to the R. Okay, and basically I have this surjection which will give me which gives me this embedding. Okay, so I just need to figure out the kernel of this. So the homogeneous ideal of in S dot define so cutting out y tilde is so what I will get is there is the ideal T T times AT in degree 0 plus T times AT in times U in degree 1, and then the higher in the higher degrees, basically what I will get is I just I leave out. So okay, let me write the next one. So T times I square, no, so T times I plus T square AT times U square, and so on. Okay, so so in general the rth term will be T times I to the power R minus 1 plus so on up to T to the power R AT U to the R plus. So okay, that is my idea. And so now again since I'm a little short on time, again I will just write down what it is. So so the generator for this you can check for the, so if I take this ideal, I localize and I go inside this patch, okay, then you can see that in B plus of AU this is cut out by so y tilde is cut out by TU over AU, okay, so this is now degree 0, which is basically T over A. Okay, and so now observe that A over 1 Okay, so this corresponds to the exceptional divisor times t over a, which corresponds to y tilde. This is equal to t over 1, which corresponds to rho inverse of infinity. Okay, so this is what is happening in this particular patch. Now we still have to deal with one more patch, which is where t is not equal to 0. So in d plus of tu, actually one can check that. So what happens? Yeah. So this y tilde, the ideal sheaf corresponding. So this is basically so inverse of okay. So SST S dot of t. This is equal to the sum or r equal to r greater than equal to 0 of I. So if I take this and I localize at t and look at the yeah, that seems okay. And then if I so now I want to see what is s dot t by t times s dot t. So this since I mean in s dot t the only part of rho inverse infinity that is there is basically what is left of the exceptional divisor after leaving out after removing the removing y tilde. So I just want to see that this is equal to the cone. So this is equal to, I think I'm making some kind of mistake, but yeah, it is what it should be. It should be that, but I'm just trying to see why it is not coming out like that. So because it should come out to be the sum of I to the r by I.
Already proved what all of it is, and already proved what set infinity. Therefore, the complexity is.
Yeah, that is true. But I was just trying to see that. Yeah. Anyway, maybe we'll talk. I think we are almost out of time, so maybe we can figure this out in the discussion. Yeah, it's actually something simple, but I'm somehow missing this.
Localization, they typically minus r plus y plus 2 that about that's why the RMD is.
What happened?
I think I was just trying to see why when you that actually r modulo actually r plus 1 comes because since it's a homogeneous localization.
Yeah.
So when
Okay, but I mean, it's something simple. I think it's sort of clear enough in the book, but I don't. No?
You are knowing of this ideal I comma t.
Yeah. Yeah.
So it becomes locally principal on the block.
Yes.
On this open set, when you are localizing t,
Yeah, it is generated by t.
it is generated by t.
Yeah.
And therefore, when you are going modulo t, you are basically going modulo it is that homogeneous ideal.
Chetan, that denominator is shifted by 1.
Yeah.
All the time, and that is what is being used. In the grading, denominator is shifted by 1 to the right. And quotients are leaving 1, 0.
Yes. Yeah. This is basically yeah. This is basically I comma t. I mean, the ideal t is basically I comma t, but now everything has gotten shifted. Yeah. But. So, but then why is this? I mean, okay, it's now that gets the indices right, but then why is this I and not? Why is this I and not I comma t?
Because by that shifting.
Oh yeah, t. I'm killing t. So yeah. Okay. Yeah. Okay. So yeah, I mean that basically. shows that there is such a flat family which at over 0, so there's a flat family over P1 which over 0 is giving you your given embedding, and at infinity it is giving you the embedding of X inside the normal cone. So yeah, maybe this we can use next time.